graph. Now we all know graph, isn't it? We all know graphs. Now there are some applications, okay, where things can be easily represented using graphs, where it is very difficult to represent those things without graphs. Take an example. We have multiple. If you have multiple airports and you want to see whether there is a connectivity, okay. Or take an example of a map. In a map, what you do if there are multiple cities in a state, then if there is a road or train, okay. In that case, what you do, we to check whether there is a connectivity between different cities. We draw those cities and we draw a line, okay, either it's a curve or straight line, a line between those cities. So a graph is a important data structure in computer science, where there are many applications where this is used to represent some data. What type of data? Like data where we need to check connectivity. In computer terms, we mostly take an example of computer networks. In computer networks, what you do? Suppose at KIT, if we want internet, so we buy internet either different ISPs. ISPs is what? Internet service provider. Like we have BSNL, Reliance Jio, Airtel, and their offices will be there. And at their end there will be one router, and at our end we will have one more router. So different routers, switches, and all the networking diagram. Now this is drawn again in terms of graphs. So here routers represent nodes or vertices, and the connectivity or link represent an edge. So what is edge and vertex? In if you when we define graph, how the graph is defined? A generalization of the simple concept of a set of dots or links, edges or arcs. So we have nodes or vertices, okay, and we have a connectivity between those nodes or vertices. So I will not use node now. I will use only vertex. So we have different vertices which represent some entity, and if there is a connectivity between those entities, then that is connected through links or edges or arcs. So I will refer those entities as vertices V, and those lines as edges. Okay, henceforth what I will refer, a graph G equal to V comma E, where V comma E are two tuples, where V is a tuple of a different number of vertices which are present in the graph, and E is a number of edges which is connected among those vertices. So representation, graph G equal to V comma E consists set of vertices denoted by V or V of G, and set of edges E, or we sometimes represent as edges of G, E of G. Now, what are different graphs we have? We have broadly classifying like a directed graph and undirected graph mainly. So, in a directed graph, the edge between two vertices will have a direction. Now, take an example: directed ordered pair of vertices represented as U comma V, directed from vertex U to V. In this U to V, what is U here? U is a tail and V is a head. Okay. In a directed graph, the direction can be represented by tail and head. Okay. So U is a tail and V is a head here. Now, in undirected graph, there is no direction marked on the edge. So either it can be considered U to V or V to U. Both is possible direction here. Whereas in directed graph, when I say U to V, I cannot go back from V to U. So what is go? In general, informally, I am saying go back. It's not go back. It's called as traversing. Traversing means traveling or visiting from one node, one vertex to other vertices. So here U to V, I can traverse U to V, but I cannot traverse from V to U back, because there is no edge which has a direction from V to U. Now take an example, the other one, undirected graphs. What are undirected graphs? When in a graph between vertices, when there are edges, and if those edges do not have a arrow or a direction symbol, then they are called undirected graph. Unordered pair of vertices represented u comma v disregards any sense of direction and treats both end vertices interchangeably. So I can represent this edge as u to v or v to u, v to u. So this is called undirected graph. What is loop? A loop is an edge whose endpoints are equal. That is starting point and the terminating point. If it is same, that is called loop. So on a vertex u, if I have a edge, okay, which starts with u and comes back to u, that is a loop. So an edge joining a vertex to itself is called a loop, represented as u comma u or just u. Okay, what are multiple edges? Two or more edges joining the same pair of vertices is called multiple edges. So if I have u v here, u and v, u and take undirected graph here, u and v two vertices, and I have one edge here. If I can write two more edges on the same u to v, that is called multiple edges or sometimes multigraph. Now simple undirected graph. Okay, a simple undirected graph consists of V, a non-empty set of vertices, and E, a set of unordered pair of distinct elements of V called edges. So representation of example G equal to V comma E. So here what are vertices? U, V, W. What are edges? U, V, U, W and W, V. U, V, V, W, U, V, V, W and W, U, W. So three edges and three vertices, as it is a connected graph as well as it is undirected graph. So a simple graph, undirected graph, consists of V, a non-empty set of vertices, and E, a set of unordered pairs of distinct elements of V called edges. What is multigraph? See this. Between U and V, there are multiple edges. So that is called multigraph. In a graph G, V, comma E, multigraph consists of set of vertices V, set of edges E, and a function f from E, u to v, u comma v, v vertices u not equal to v. The edges e1 and e2 are called multiple or parallel edges if function e1 equal to function f of e2, which is represented as v, u, v, w, and what are the edges? e1, e2 and e3. So in simple words, if between two vertices, if there are multiple or parallel edges, that is called multi-graph. Okay, geodograph. Okay, we don't need geodograph. I'll just skip this. Directed graph is that there is a direction between these, edges between vertices. That is called directed graph. So mainly we will think of directed graph and undirected graph in our data structure terms. So if directed graph G V comma E, set of vertices V and a set of edges E that are ordered pair of elements of V. So representation G comma V, how we will represent a graph G V comma E. Here what are vertices? V equal to set of U V W and E edges are set of, take each edge as they are directed, we will represent them with brackets. So how many edges we have? U to V, that is the first one, V to W, that is the second one, and W to U. I cannot write back V to U because there is no directed edge from V to E. Directed multigraph, you can see this simple terms E1, E2. There are two edges which are parallel edges between two vertices. That is called multigraph. If one of the edge is reverse order, then that cannot be the multigraph. See this G of V comma E consists of set of vertices V, set of edges E, and a function from F from E to UV and UV, another one UV, which are a part of V. The edges E1 and E2 are multiple edges if f of E1 equal to f of E2, because E1 E2 they are same. If I have direction U2 V E1 and there is I have a other edge which is in reverse order V2 E, then that cannot be multigraph. Now this is directed multigraph. Okay, what else we need? Basics of graphs. Suppose U and V are adjacent. Now what are adjacent vertices? U and V are adjacent if U comma V is an edge. E is called incident. E is called incident with U and V. Edge is called incident. U and V are called endpoints of UV. So what are adjacent nodes here? You can see this in this particular U and V. U is adjacent to V and V is adjacent to U because it is undirected graph. Okay. What is incident? E is called incident. Edge E is called incident into U as well as V. Degree of vertex. What are degree of vertex? A degree of vertex is a number of edges which are connected to a particular vertex vertex where in undirected graph, because there is no direction here. So degree of vertex, degree of V, the number of edges incident on a vertex. A loop contributes twice to the degree. Why? Now suppose there is no loop here. Suppose if I on K if I write a loop, then what is why it is called twice the degree? Because one point is going out and one is coming out. So 2 degrees. What is pendant vertex? Degree of V equal to 1. If V and W, see this, in V and W we have only one edge coming into it and there is nothing which is going out. So only one edge connected to this. So these are called pendant vertex. Okay, these V and W are called pendant vertex where degree of V equal to 1. What about degree of U? Degree of U equal to 2 because there are two edges. One is U to V and other is U to W. What about K? Isolated vertex. All isolated vertex will have degree of 0. Degree of vertex K is 0 because there is no edge which is going out or coming in to this particular vertex. Okay. Some more terms for the edge UVW. Okay, for the edge UV, U is adjacent to V or V is adjacent from U. Now this is directed graph, so that's why how to read this? There is a edge from U to V. U is a tail, V is a head. Now see this, for the edge UV, U is adjacent to V. Okay, U is adjacent to V or V is adjacent from U. Okay, so E is initial vertex and V is terminal vertex. What is in degree in that graph? The number of edges coming into a particular vertex is called in degree. Now in degree of V is how much? So we have only one edge which is coming from U to V. So incoming edge is only one. So in degree is 1. What about out degree? Out degree of V is also 1 because there is only one edge which is going out. What about out degree of U? There are two edges which are going out of U, U to V and U to W. So out degree of U is 2. What about in degree of U? There are no edges which are coming into this particular vertex U. So in degree of U is 0. Take this. Out degree is what? Number of edges for which U is initial vertex. So U, we have two edges which is initial or two edges which are going out of U. So that is, it is called out degree of U is 2. Now, do we have loop here? No. A loop contributes 1 to both in degree and out degree. If I write a loop V to V, then the line going and coming in for directed graph. So both in degree will be added 1 extra and out degree is also 1 extra. Representation example for V, U, V, W, 3 vertices. What are edges here? Edges are U to V, U to W and V to W. UW, VW and UW. What about degree of U? Degree of U is in degree is 0. So we write a degree minus here, that is in degree, and degree plus out degree of U equal to 2. Now in degree of V is how much? 1. Out degree of degree plus out degree of V equal to 1. And degree minus raised to minus we write here. This is in degree. In degree of W is how much? 2. Because two edges are two edges terminate at W, and there isn't a single edge which is going out, or initial W is not a initial vertex for any of the edge. So that's why there is no out degree, only in degree. So in degree of W equal to 2 degree plus out degree equal to 0. This is not U, this is W. Okay, we know, don't need this theorem and all. Leave it. So what is complete graph? What is complete graph? Kn is a simple graph that contains exactly one edge between each pair of distinct vertices. Now representative of K1, K2, simple graph. Let me take simple graph K1, K2, K3, K4. These are simple graphs. A vertex. What is a complete graph? If in a graph, if I have a edge from every vertex to every other vertex, that is called complete graph. Now take this example. We have single vertex, so you don't need to have a loop. So it's a simple graph. If there is a loop, then that is called differently. So in simple group, there won't be any loops. Now take this K2. I have a edge from node 1 to node 2. Okay, what about K3? Again, you can see this. Every vertex can be connected to other vertex. Take this as A to B, A to C. We have two edges to both the nodes. What about B? It's the same thing. If there are 4 nodes, then you can see that if I represent it as node 1, 2, 3, 4, 1 to 2, 1 to 4, 1 to 3. So every vertex can be connected to other vertices with dedicated edge. So this is called complete graph. In a complete graph, all vertices will have edges to other all vertices. So that is called complete graph. What is cycle? Now again here the second one Q2 is not a cycle. If but other things can be a cycle here. K3, K4 they can be cycles. So let me see what is cycle first in a graph. Cycle Cn if nodes are more than 3, because in node if nodes are 1 and 2 there cannot be any cycle. So if in cycle where nodes are vertices are more than 3 or like or more than greater than or equal to 3, which consists of n vertices v1 v2 v3 to vn and edges v1 v2 v2 v3 v3 v4 vn minus n and vn to 1. What is the meaning here? Meaning, suppose now take this 3 vertex 1 2 3. I can go from 1 to 2 and 2 to 3. If I can come back again from last vertex to the initial vertex, that is called cycle. Again you can see this. You take any of the node, I can visit all the vertex and come back again. So this is called cycle. Wheels, okay, we don't need wheels then cubes and all. Let me take some other one more presentation. Okay, now is it over all this thing? I think this is over. No, all it is covered. It is covered, I think. Was it covered earlier in DMS? Hello? Someone can reply. Am I audible? Am I audible? Yes, I am audible. But was it covered in DMS? Yes, it is covered. These all things are basic things. Let me cover some more things. Maybe we have left something. Okay, no. Okay. So what is graph? A graph G consists of two sets. What are two sets? Set of vertices, set of edges. So a graph is a finite, non-empty set of vertices V, a finite, possibly empty set of edges E of G. See, in a given graph, V vertices cannot be empty, where E can be empty. Why E can be empty? If in a graph I have single node and no edges, no loops, then it can be edges can be empty. Whereas vertex, at least I should have one vertex. So that's why a graph consists of two sets. The first set is a finite non-empty set of vertices, and second set is possibly not empty set of edges E of G. So we write or represent the graph as G comma G in bracket, we write V comma E, where V is the number of vertices present in graph and E is number of edges present in a graph. What is undirected graph? If there is no direction mark on the edges, then that is called undirected graph. And undirected graph is one in which the pair of vertices in edge is unordered, v0 v0 comma v1 equal to v1 comma v0, whereas in a directed graph is one in which each edge is a directed pair of vertices. So v0 v1 is not equal to v1 v0 if there is no direction. What about this one here? The starting point from where it is going out, the edge is going out, that is called tail, and where it is incidenting, incoming to that particular vertex, that is called head. If I write here v1 v2, v1 will have the edge is tail here, and for v2 it is a head. Take example for graph. So we have a graph, this is called complete graph, where every vertex is connected with other vertex with dedicated or connected edge. Okay, so v1 0 0 to 1 0 to 2 0 to 3, there is a edge 0 to 1 0 to 2 0 to 3. Likewise 1 2 3 1 0 1 2 1 3 3 1 3 0 3 2, like 2 0 2 1 2 3. What about G2? G2 and G3 are not complete graphs because from 0 to 3 is there any edge? No. 0 to 1, 0 to 2 I have edges, but 0 to 3, 0 to 4, 0 to 5, 0 to 6 there are no edges. Now you can see this example for the first one, G1 graph. V of G1 equal to what are vertices here? 0 1 2 3. What are edges here? 0 1 0 2 0 1 0 2, then 0 3. 1 1 2 1 3, because why we cannot take 1 0, already 0 1 is taken, that's why 1 0 cannot be read here. So 1 2 1 3, then what is the left here? The last one is 2 3. So how many edges here total in a complete graph of undirected graph? If it is undirected graph, then number of edges will be n equal to n minus 1 by 2. So here in this case 1 2 3 4 4 4 nodes we have, four vertices. Then what is here? 4 4 into 4 minus 1, which is 3. 4 3s are 12 divided by 2, which is equal to 6 edges. You can see that 1 2 3 4, and we have two more edges. For a complete graph of, if it is undirected, then total number of edges will become n equal to n minus 1 by 2. And if it is a directed graph, then it will have n equal to n minus 1 edges. Why not divided by 2? Because now each edge in undirected graph is represented by two edges in directed graph. Okay. So these are incomplete graphs. This is complete graph. If a given graph has edges from every node to other every node, then that is called complete graph. Complete graph. A complete graph is a graph that has the maximum number of edges. So I cannot have more than this. So these are the maximum number of edges which are possible in a graph. So a complete graph is a graph that has the maximum number of edges. For undirected graph with n vertices, the maximum number of edges equal to n into n minus 1 divided by 2. For directed graph, it will become n equal to n minus 1, n into n minus 1. What is the example here? Example, G1 is a complete graph. If you see this, the first one, G1, it's a complete graph. Adjacent and incident. If v0 v1 is an edge, v0 v1 is an edge in an undirected graph, then v0 and v1 are called adjacent nodes or adjacent vertices. Adjacent vertices. The edge v0 v1 is incident on vertices v0 and v1. What do you call it? We call them, we write them as the edge v0 v1 is incident on vertices v0 and v1. So common word here, because it's a undirected graph. Whereas if it's a directed, if v0 v1 is an edge in a directed graph, v0 is adjacent to v1 and v1 is adjacent from v0. You can see this, the difference between here and here. In undirected graph, you call v0 v1 is an edge. In an undirected graph, v0 and v1 are adjacent. Whereas in directed graph, you call v0 is adjacent to v1 and v1 is adjacent from v1 if there is a edge directing from v0 to v1. The edge v0 comma v1 is incident on v0 and v1. example of graph with feedback loops and a multigraph. If take the first one, 0 to 0, we have a arc, so that's why this is called a loop. It's called a loop. Okay. And what about multigraph? Between 2 and 3 in the figure B, between vertex 2 and vertex 3, there are 3 lines here, 3 edges. So that's why it is called these are multi edges. So it is also called as multigraph. In a graph, if between two vertices, if there are multiple edges, then that particular graph is called as multigraph. Multiple occurrences of the same edge here between 2 and 3. So what is subgraph? A subgraph of G is a graph G dash such that vertices of G dash is a subset of original vertex G, and edges of the second G dash is a subset of EG. A path, what is path? Path is when traversing, we need to see what is the path. So what is path here? A path from vertex VP to vertex VQ in a graph G is a sequence of vertices. Suppose my starting vertex is VP and the ending is VQ. Then if we have a direct line, I can see VP to VQ. If there are in between there are different vertices present, then I can write all the vertices which are there in the order VP, VI1, VI2, VIN, then VQ, such that VP to VIN, I1 to I2 there is edge, and I2 VI2 to VI3, and the last IN to VQ. So are edges in an undirected graph. The length of path is the number of edges on it. So let me take some example. Okay, maybe next here. So we have a graph G1. What are subgraphs? You can see this is a subgraph. The first one is a subgraph, first, second, third, fourth. All are subgraphs of G1. Some of the and this is here 0, 1, 2, 3 vertices. Now 0 itself is a subgraph of G3. Second one, 0 and 1. Also this is also again a subgraph of G3. Again this one is a subgraph of this, and this is the last one, fourth one graph. This is also a subgraph of G3. Simple path and style. What is simple path? A simple path is a path in which all vertices except possibly the first and last are distinct. Okay, every verse are distinct, then that is called simple path. What is cycle? A cycle is a simple path in which the first and the last vertices are the same. If I start with the vertex V0 and visit V1, V2, V3, V4, all the vertices, and come back again to V0 itself, then that is called cycle. So in a cycle is simple path in which the first and the last vertices are same. First and last vertices same. What about in between vertices? They will not repeat. Okay, we will visit only once all the vertices. In an undirected graph G, two vertices V0 and V1 are connected if there is a path in G from V0 to V1. So in a number of vertices in a graph V0 to V1, we call V0 and V1 in a undirected graph G, two vertices V0 and V1 are called are connected if there is a path. If there is a path between V0 to V1, maybe it's a single path or a single edge, or connected edges between. There are multiple vertices which are present. By traversing or visiting them, I can reach from V0 to V1. What is an undirected graph? Is connected if for every pair of distinct vertices Vij there is a path from I to J, Vi to Vj. What is these are connected graphs? You can see that from 0 I can reach 1, I can reach 2, I can reach 3, and everywhere. Whereas G1 is a complete graph. What about second graph G2? It is not a complete graph, but still it is a connected graph because there are no edges where I cannot reach. See this 0, 0 to I can reach 1, I can reach 2, I can reach 3 by 0, 1 and 1, 3. So I can reach 3. What about reach 4? I can reach 4, I can reach 5, 0 to 5, I can reach 6 by 0 to 6. What about take any random again one more vertex, suppose take 4. So with 4 I can reach what? 4 to 3 I can reach, 4 to 1 I can reach, 4 to 0, Again 4 1 0 2 5 4 1 0 2 6. So I can reach all the edges. I can reach from any vertex to any other vertex. So this is called connected graph. Okay. Uh, Connected component. A connected component of an undirected graph is maximal connected subgraph. A tree is a graph that is connected and acyclic. So you take this example. So this graph is a tree which is acyclic, means there is no cycles here. I cannot, there is no cycle, so I cannot, I don't have any cycle here. Cycle means what? To start with one particular vertex, and after reaching some other vertex, if I can come back to the same vertex, that is called cycle. So tree is not a there are no cycles, so tree is also called as a cyclic graph. A directed graph is strongly connected if there is a directed path from Vi to Vj and also from Vj to Vi. A strongly connected component is a maximal. Okay, leave it. What else we need? We need degrees. Okay, so what is degree? The degree of vertex is the number of edges incident to that vertex. If it is undirected, then the number of edges which are incidenting, that is called the number of degrees. And if it is a directed graph, then we have in degree and out degree. The in degree of vertex B is the number of edges that have V as the head. Okay, that is the edge is pointing to that particular vertex, that is head. In degree. Out degree, the out degree of vertex V is the number of edges that have V as the tail or edges going out of the vertex. So what is the last here? If di is the degree of vertex I in the graph G with n vertices and e edges, the number of edges is equal to sum of 0 to n minus 1 degree of vertices divided by 2. Okay, let me later we'll take some example. What is degree here? Degree of 0 equal to how much? See this 1, 2, 3. 3 edges connected to this. This is an undirected graph. So degree of 0, degree of 1, degree of 2, all the vertices is equal to 3 as it is a complete graph and strongly connected graph. Now take the second one. So this is a directed in a directed graph. Second one is undirected. So how many edges here? 0, 2, 1. Uh, for 1 it is 3 because we have 0, 1, 3, 4 and 4, 1. So 3 is again 3 here, and at leaf nodes always in 3 will have only one edge. So degree is 1. What about if it is directed? If it is directed graph, then we will have in degree and out degree. So for vertex 0, one edge is coming into and one edge is coming out. That is, it's a head. There is a head of edge to 0, one head, and we have one more edge which is the tail. So in degree is 1, out degree is 1. What about 2? From a vertex 2, there is no edge which is going out, or there is no edge where it is having a tail at 2. So we have only incoming edge. So in degree is 1. There is no out degree here. Out degree equal to 0. So we'll see how the graphs are represented in computer. How the graphs are represented? Graphs are represented in three ways. One is adjacency matrix, second is adjacency list, and third is adjacency multi-lists. So we will not use multi-list. We will take only two. The first two. The first one is adjacency matrix, and second is adjacency list. So the simplest one is adjacency matrix. Let me explain both the way of representing a graph in computer storage. So what is adjacency matrix? Let G a graph, V comma E be a graph with n vertices. Then the adjacency matrix of G is a two-dimensional n by n array, say adjacency matrix. If the edge Vij is an edge of graph G, adjacent matrix Ij equal to 1. If there is a edge present between vertex Vi and Vj, okay, two vertices, then we will write in the matrix in adjacent matrix I comma j equal to 1. If there is no edge, such edge between edge in E of j, adjacent matrix for I j will write 0. I will take an example and explain it to you later. the adjacency matrix for an undirected graph is symmetric. Okay, the adjacency matrix for an undirected graph is symmetric. The adjacency matrix for a digraph or directed graph. Directed graphs are also called as digraph. So digraph need not be symmetric. Now take an example. So 0, 1, 2, 3. Now we have so how this can be represented in with adjacency matrix? Take this here. So how many vertices we have? 4. Then my adjacency matrix will have 4 by 4, 4 rows and 4 columns. Okay. So you can see this. Take you have to write here 1, 2, 3, 4. All the or 0, 1, 2, 3 edges here. 0, 1, 2, 3. Do we have 0 to 0 loop here? There is no loop. So 0 to 0, there is no edge. So we have written 0. What about 0 to 1, 0 to 2, 0 to 3? See this 0 to 1, there is a edge. I will write it as 1. 0 to 2, 0 to 3, there is a edge. I will write it as 1. So except the diagonal element, you can see that everywhere we have written 1. So take this example 3. 3 to 3, is there any edge? No. But 3 to 1, I have 3 to 0, 3 to 1, and 3 to 2. We have edge 3, 0, 3, 1, 3, 2. I will write it as 1. If there is no edge, I will write it as 0. What about the second one? Take the second G2 graph. Here, the adjacency matrix will be 3 by 3, 0, 1, 2, 3. So 0 to 0, no loop. So it is 0. What about 0 to 1? As it is directed graph. So 0 to 1, I have a edge. I will write it as 1. What about 0 to 2? 0 to 2, there is no edge. So that's why I will write it as 0. What about 1? 1 to 0? Yes, 1 to 0, I have edge. I will write it as 1. 1 to 1, there is no loop. So it is 0. What about 1 to 2? 1 to 2, I have edge. So I will write it as 1. What about 2? There are no edges which are going out, or there is no edge which has a tail at 2. So there is no outgoing edge here. So that's why 0 to 0, there is no edge. 0 to 1, 0 to 2, there is no edge. So I cannot write it here. If it is undirected graph, I could have written here. Okay. Now what else we have? 1, 2, 3, 4, 5, 6, 7, 8. You can see this. There are 8 vertices. Okay. Now why these are symmetric undirected graph? Because these are symmetric. If we just transpose this 0 to 111, you can see this 0 to 111. Okay. Edge will be when I have a edge from 0 to 1, it can also be written as 1 to 0. So that is the symmetric here. So you can see this in second graph 0, 1, 2, 3. You can take the half part, but this graph is disconnected graph, because see there are some edges where I cannot reach 7, 6, 5, 4. 0, 1, 2, 3 cannot reach 4, 5, 6 edges. So this is a disconnected graph. So what are merits of advantages of adjacency matrix? From the adjacency matrix, to determine the connection of vertices is easy. Determining the connection between see this, what are advantages or merits of adjacency matrix? From the adjacency matrix, to determine the connection of vertices is easy. The degree of vertices is what? Adjacent matrix I comma j. If you just you can read this all, then I will directly get for a particular vertex what is the degree. So for what is the degree of here in the first case? So you just add 1, 2, 3. So 3 is the degree for. So all the nodes it is same. Now what about here second graph G2? You can see that vertex 1. What is the degree here? If you just count number of ones present here, that is the degree. 1 and 1, 2. So 2 is the degree. You can see this here. 0 to 1 for node 1. 0 to 1, that is for undirected graph. Undirected graph, I have to count this. For directed graph, I have to count the line which are coming in. Okay. The degree of vertex here. The degree of vertex is adjacent matrix, read all J. For digraph or directed graph, the row sum is the out degree. The row sum is the out degree. while the column sum is the in degree. Let us check again here for vertex 1. Vertex 1, row sum and column sum. What are column sum here? For a given vertex 1, okay. For a degree, for a diagonal graph, the row sum is the out degree, while the column sum is the degree. For individual edge vi, j2 n minus 1, adjacent is ji we have to read. So what is row sum here? For degree 2, row sum is 0, means there is no outgoing edge. What about 2 here? Is there is one incoming edge for column sum. Let me read it again. For a diagonal graph, the row sum is the out degree and the column sum is the in degree. Okay, take this. The row sum is the out degree. Out degree, row sum, column sum, in degree. For this diagonal graph, if you see the vertex 2, what is row sum? Row sum is 1, 2, 3, 0 it is. Okay, you have to count number of ones present here. So this 0, that means there is out degree 0. What about read the last column? Column sum is the in degree. So we have 1 here. That means there is the one in degree is 1. Take example of the second vertex 1. So what is the row sum here? 1 plus 1, 2. That means 2, the out degree is 2. What about in degree? See this, read this column sum. Only one bit, we have 1 at only one place. That is 1 in degree is only 1. Now data structures, that was the adjacency matrix. Later we will take one more example, and I will show you how to draw that adjacency matrix or adjacency matrix. We'll take one graph and we'll try to represent it in both in adjacency matrix as well as in adjacency list. Take this one more. Data structures for adjacency list. For data structures for adjacency list. Each row in an adjacency matrix is represented as an adjacency list. Now we will represent this by graph, then you will understand it properly. Now this is the second way of representing a graph with adjacency list. Now take this, these are same graphs here, 0, 1, 2, 3. Now it is represented 0, 1, 2, 3. So 3 rows are for 3 nodes. All the vertices we represent 3 rows. So that is written here. Each row in adjacency matrix is represented as an adjacency list. Now initially we will have number of rows equal to number of vertices 0, 1, 2, 3. Then from there we will have linked list. Suppose 0, I have 1, 2, 3, 0 to 1, 0 to 2, 0 to 3, there are links. So I will write 0 to 1, 1 is again connected to 2, 2 is connected to 3, and at last we have null. Likewise in all the things. Take this second one. It's a directed graph. I want to represent this in adjacency list. Then first thing what we should do, I should write number of rows 0, 1, 2. How many vertices? 3. 0, 1, 2. So I will have 0, 1, 2, 3 rows. Then check whether there is a outgoing edge from 0 to 1. Yes, I have 0 to 1. So I will write 0 to 1, 1 as a list. Okay. Adjacency list. What about 1? 1, 1 to 0 and 1 to 2. There are 2 edges here which are outgoing. So I will write 1 to 0 and 0 to 2. What about 2? 2 has only incoming edge, but there are no outgoing edges. So I will write just null. Okay. So this is how to represent a directed graph in adjacency list, and this is a way of representing a undirected graph in using adjacency list. You can take this again here 0, 1, 2, 3. Just go through this and you can understand. I will upload this one later in the Moodle. So what are different operations? Degree of vertex in a undirected graph. Edges, okay, compact representation. Now this is enough. Now what else we have in this graph? What else we need to note? These are some basics. and I know that all this is covered in the DMS. So basic terminology and representation of graphs using adjacency matrix, that is enough. Then storage representation. Then I will see graph traversal techniques. So next lecture, what I will do, we'll take one example. What I will do, let me take one example where I will represent a graph using adjacency matrix and adjacency list. Okay. So we'll take one example of this, and then next lecture we will see how we can traverse. So we'll see both BFS and DFS, breadth first search and depth first search. So how many participants we have today? Participants 46. Why the strength is less today? Okay, let me cover this one. Am I audible? Is screen visible to you? I hope screen is visible to you. Is it visible? Yes, yes. Okay, okay. Now let me take one example graph, and we'll try to represent it in adjacency matrix as well as adjacency list. Okay. Now take, suppose I have a graph 1, okay, 2, 3, 4, 5, and okay, let me take only this. This is enough. And I have edges here 1 to 2, 2 to 3, 1 to 4, okay, 4 to 5, and 3 to 5, 2 to 4, and 3 to 4. Now, when we want to represent using this adjacency matrix, how we do it? We do it, okay, what is adjacency matrix? Adjacency matrix. Okay. Now, in adjacency matrix is a matrix of a size of n into n, where n is number of vertices. So n is how much? N is what? N is number of vertices. Number of vertices present in a graph. Vertices present in a graph. Present in graph. So what is n here in our case? N equal to 5. So matrix will be, adjacency matrix will be A, adjacency matrix A, adjacency matrix will be 5 by 5. Okay. Now let me draw here nodes 0, 1, 2, 3, and 4. No, this is not 0. No, we'll start with 1. Let me take it 1. Okay. So 1, 2, 3, 4, and 5. So again you have to write 1, 2, 3, 4, and 5. So if I can draw this here, so this will be the matrix. Okay. Now, how we are going to represent in adjacent matrix? I will write either 0 or 1. If there is a link between vertices, I will write it as 1. Let me take this one here. This is 1, isn't it? Okay. Do we have loop here between 1 to 1? No, no. At 1 to 1, do we have anything? No. So it will, I will write 0. Likewise, 2 to 2. So what is loop? Loop, take this example. Suppose I have a node called 6. Okay. So if I can write like this, this is called loop. Means a edge starting with that same node and will end with end at the same edge. So that is called loop. So we don't have loop here. So you don't have loop. Okay. So how are we going to represent? 1 to 1, 0. 1 to 2, I have a edge 1. What about 1 to 4? See this 1 to 2, I have a edge. Then 1 to 4, I have edge. 1 to 4. What about 1 to 3? 1 to 3, I don't have edge. I will add 0. 1 to 4, I have edge 1. What about 1 to 5? There is no edge. I will add it as 0. What about 2? 2 to 0, 2 to 1, as it is undirected graph, you can write in both the ways, this way also and this way. Okay, so 1 to 2, 2 to 1, 2 to 1, I have edge 0. What about 2 to 0 or 2 to 2? There is no loop, 0. 2 to 3, I have edge. 2 to 4, I have edge. 2 to 5, there is no edge, 0. Then 3, 3 to 1, no edge. 3 to 2, 1. 3 to 4, I have edge. 3 to 5, 3 to 3, no, it is 3 to 3 is, there is no loop. 3 to 4, I have edge, and 3 to 5, I have edge. What about 4? 4, 4 to 1, I have edge. 4 to 2, there is a edge, I'll add as 1. 4 to 3, there is a edge. 4 to 4, no loop, 0. 4 to 5, there is a edge. What about 5? 5, you can see that there is only 1 and 2. 2 edges are there. Okay. So 5 to 0, 5 to 0, no edge. 5 to 2, no edge. 5 to 3, 5 to 4, there are edges. And 5 to 5, there is no loop. So this is a adjacency matrix. So we are going to represent this particular graph. Okay. This graph V with V comma E. Okay, is represented here in this format, adjacency matrix. Adjacency matrix. Now what is V here? V equal to, V is number of vertices 1, 2, 3, 4 and 5. And what is E? E edges equal to, what are those? 1, 2, 1, 4. So you have to write all those 1, 2, 1, 4, like this. You have to write all the edges. Understood? Any questions? How to represent a graph in adjacency matrix? Now we have to write a program for this. Coding is altogether different, but at least you understood, no, pictorially how a graph can be represented in adjacency matrix. Okay. Now let me take how we can represent this using adjacency list. Okay, we'll take the same graph. I'll take the same graph. Adjacency list. Okay. Now adjacency list here. Now I forgot to represent. Tell you one thing. What was the size of adjacency matrix? As adjacency matrix was 5 by 5. Whatever node we have, node n size equal to what? Size of G in adjacency matrix is n into n. N into n, because those many rows and columns, isn't it? So the space complexity is theta of n square, because it is n into n number of vertices. If there are 4 vertices, 4 to 4, 4 rows, 4 columns. So 4 square, like 5 square. So this is space complexity of adjacency matrix. Okay. Now we will represent the same graph using adjacency list. So initially what we should do, we will write all the nodes, 1, 2, all the vertices 1, 2, 3, 4, 5. Okay. So this is how it is. So we will have 5 rows: 1, 2, 3, 4, and 5. Okay. Now then, you should draw. You should write list. So check whether we have 1, 2, 3. There is a node. Yes, I have 1, 2, so that's right. 4, 4. I will know this is 1, 2, 4. 2, 2 is the 11. This is 2 first and third. Now 3 to 4 and 3 to 5. 1, 2, 1, 2, and is the 1 to 4. 2, 3 edges here. 2, 2, 4 to 1, 4 to 2, 4 to 3, 4 to 5. So all the edges are there. So I will draw 4 nodes. 1, 2, 3, and 5. What about 5? At 5, I have only 2 edges. 4, 5 to 4 and 5 to 3. So I'll add 5 to 3, 5 to 3, and 5 to 4. So we have to connect this. And at last node will have null here. Null. Null. So this is how it is represented using adjacency list. So you will create a matrix with the number of number of rows, and each row will have connectivity edges as a linked list. So how many linked lists will be there? If there is, if suppose there are 5 vertices present in a graph, then I will have 5 different linked lists representing from each node connectivity. Any questions? Any questions? What is the time complexity here? Time complexity here, sorry, time, not time, space. Space complexity, time complexity. Space complexity is how much?